Hello. We are going to talk about explaining grammatical gender predictions. So the motivation for our work comes from when people try to learn a new language, they often struggle with understanding how the grammatical gender assignment works in the new language. So, for example, in French, the word person or person is feminine. And in order to use French correctly, you need to say la personne or and not le person. In addition to in language learners, another aspect of grammatical gender comes into play in how it affects our social views and biases. For example, applying the Sapir-Whorf hypothesis in this context tells us that our grammatical gender influences the way we look at things around us, and also the other way around. The society has an impact on grammatical gender. So, for example, in Swedish, historically we had separate masculine and feminine genders, but today we just have a common gender in the standard Swedish. Also, people show preference for words like police or police person, which are gender neutral, over words like policeman. So we are interested in explaining, understanding the role of form and semantics in gender assignment so that we can address these issues better. Right, so linguists have a long history of studies where rule-based approaches have been discussed for studying the role of morphophonology and semantics in determining grammatical gender. An issue with this approach is, of course, this is not does not easily yield universal rules and is also manual, so it's not easy to scale. And also, computational linguists have recently looked at making predictions using contextual information, but that's not very good at giving us the explanations. So, for example, in French, you if you just give an explanation that person is feminine just because you saw la person in context somewhere, that's not a good explanation for why it is feminine. Right. So to summarize, we compare rule-based models and neural models or black box models, which are more scalable and also more accurate in practice in terms of making predictions. However, the explainability is usually lacking in these approaches, and it's an active area of interest in general because it is at the core of making AI more trustworthy, fair, and ethical.
So in our work, we use dictionary, which is the lexical data extracted from dictionary. We use French language, choose words that are nouns, and have a single gender assignment, which leaves us with about 120K words. And we keep their top definition for calculating semantic features. So the first task is to do gender prediction. And for this, we investigate the role of semantics, orthography, and phonology in making the correct prediction of the word's gender. So firstly, we look at semantic features, which is generated by dictionary meaning. We used LSTM and attention-based models like XLM for generating semantic features. The next is orthographic features, which was encoded by, we tried LSTM and gram features, and we used word spelling for generating these embeddings. For phonological features, we used IPA pronunciation of the word, and similar to orthographic features, we used LSTM and n-gram features. And once we had the embeddings for these different For these different features, we use them to train a classifier to make the prediction for gender. Now, once we had a trained model, we looked at some of the results, and it appeared that none of these features alone was giving us very high accuracy. But once we looked at them together, the accuracy was boosted up. Adding semantics for sure improved the classifier's performance, whereas adding phonology did not yield that much gain given the orthography. So now moving on to the explainability aspect. So the best way to arrive at a decision may not be the best way to explain it. So for example, for a second language learner, they may need a different explanation based on their proficiency. So we propose using an auxiliary space for explanations with tunable complexity. So what does that mean? So the features for prediction need not be the same as features for explanation. Instead, a different auxiliary space can be used to generate these explanations. These explanations then can be tuned to the desired complexity. So here we see the word "roi," and we pass it through the prediction model to generate a prediction, which in this case is masculine, which is also a correct prediction. We then give this word and its prediction to the explanation model, and we set the complexity as low in this case. The output that we get is dominance, which is the explanation for this gender assignment, which makes sense here because roi, which means king, can be related to dominance, which can have masculine connotations. And then what we can do is we can tune the complexity, make it high, and this leads to the explanation model generating more detailed explanation. For example, here it can generate an explanation such as the word is not ending in E. And that is one reason why this prediction model did not make a feminine prediction. So next, we explore more general global explanations for the word gender assignments. So to do this, we do clustering on the orthographic and semantic embeddings that trained our previous black box predictor. And we did that and we clustered it such that the clusters are pure with respect to the gender of the words in them. We got about 4% error rate over there. Once the cluster IDs were assigned to these different words, we used a decision tree to predict that cluster, that particular cluster ID using the auxiliary features. So now we look at some of the results from generating these global explanations. And what we find is that some clusters are more explainable than others and also show a high fidelity. Here, fidelity is represented by the F1 score, and explainability is represented by the average decision tree path length. So in case decision tree path length is small, that means that word has a smaller explanation and therefore is more explainable. So we see that for some clusters, we were able to achieve high F1 scores at a much easier level of explainability compared to others, implying that it is possible to generate easier explanations for them, whereas for other clusters, we needed more higher and more detailed explanations to get the same amount of fidelity.
We also compare our approach of which we call global explanations with the well-known approach of local explanations proposed in the literature. So essentially what we do in this approach is that we take a subset of points which are close to the word which we are trying to explain or predict, and we train an interpretable model like a decision tree for that subset of words, and we come up with better explanations. But the issue is that these better explanations, which are uh, uh, shorter in complexity, are come at the cost of high loss in consistency across the data set.